Good morning, ladies and gentlemen. I'm from Schneider Electric industry business, and we are doing automation projects. I'm in a group which is doing standardization internally in Schneider to get a consistent offer of our large product portfolio. I would like to talk to you today about okay. I would like to talk to you about the FDT technology and how this technology could be combined with new technologies arising today as OPC UA to use mobile devices to manage field devices, and as an example, to use it together with CANopen. So I will give a short introduction of the technology itself, then about OPC UA, how we did the mapping of the OPC UA model to the FDT model, and how we are working at the moment on device management with mobile devices, and then outlook what we see as next steps in our evolution to Industry 4.0 and IIoT. So what is FDT? I think not a lot of people here in the room, when I saw all the presentations about automotive internals and so on, may be aware of that. So we talk here about automation, industrial automation, and FDT is a technology, and it means field device tool. And this technology is a specification, so it's not a software tool. The tools are done by our members in the FDT group, and it's used to manage smart devices. So the origin was in the process automation industry, where they have these field devices with thousands of parameters which you need to configure. And we also use it in other industries, like in hybrid industries, or also factory automation and energy management. And what does it allow? It allows to do a data exchange between a device tool and the physical device. And what is important, it's vendor independent. So the mechanism and the concept is vendor independent. It's also protocol independent. So we support today in the technology the main field buses. I think we are about 14 or 16 currently we support. One of them is CANopen. And what it allows then to manage different devices in a heterogeneous environment in one tool. That's the key of this technology. And as I said before, you can use it in any application because the principle is usable everywhere. So why do we want to use FDT? So you know today the devices are more and more intelligent, have more and more parameters, so they need to handle it with tools. They cannot use anymore with a screwdriver as in the past. So therefore you need tools for the engineering of these devices, for commissioning, also for optimization, maintenance, diagnostic. So, and you have a lot of these tools today, standalone single tools for each device and even each field bus. And with FDT, we are able to provide all these functions in one tool, so you can have one tool where you configure all the different devices, maintain them and commission them, whatever you need to do with your device. So that means we have many devices, we have many tools, so how do we do this integration in one tool? So the FDT concept, we compare it, this is the similarity with a printer driver. You get a printer from a manufacturer, you install this printer driver in your system and it works because there is a standard interface for printers. And here it's similar. We have an interface, the FDT interface, which is provided by a so-called FDT application, and this application integrates DTMs, so these are the drivers for field devices. So each vendor or manufacturer of such a field device provides a DTM, which is a device type manager. And the frame application is able to let these DTMs run in its environment, so it provides a common environment for the DTMs. You can configure a network depending on the application you use. It provides navigation through your application tree. You have user management, device management, and of course a database storage for all these devices in the same manner. And a frame application could be anything from a standalone tool to configure a drive, a frequency converter, for example, or integrated in a PLC programming tool or in an asset management or DCS system. So there is no specification what a frame application can or should do. This is free to the developer of such a tool using the technology. The DTM itself, so as I said, it's like a driver and represents the actual device in the frame application. The manufacturer provides this device because he talks to its device and exactly knows what this device is able to do. The DTM is installed on the frame application system, and the DTM can be used in any frame application. Due to the standardized interface, a DTM can run in different vendor engineering or asset management tools. It normally provides, of course, a graphical user interface. This is also up to the vendor of this device, how intensive, how big or small this graphical user interface is. For example, for devices which have many parameters and you want to do some diagnostics, companies offer, for example, an oscilloscope feature in the DTM where you can measure parameters in your device for diagnosis. And of course, you can then access all the device parameters with your DTM. And what is also important in the technology is your device application, your frame application can sit somewhere in the network or somewhere else, and you can access your device over network hierarchies. So you can really access from Ethernet, for example, to Profibus, to CANopen or to IO-Link or whatever. So you can really access from your tool every device in this system here with this technology. And how does this work? This is the so-called nested communication. Nested communication is the notion because you have several elements in this tree which represents the devices. You have here on the bottom level, you have the device DTM, which is related to the device. And then you have a gateway, so-called gateway DTM. The gateway DTM forwards the messages to the device. And you can have several gateway DTMs depending on the hierarchy of your plant. And the device DTM does not know, it don't need to know where its device is located. Through the interfaces, which are controlled by the frame application, the messages are forwarded automatically in this tree. And at the end, there is a communication DTM, and the communication DTM is supporting the protocol from your tool going onto the network. So, for example, here, Ethernet. But the interfaces are always the same in a communication DTM, whatever it is. If it's a CANopen, when you go directly CANopen, if it's Ethernet, IP, and other protocols, Profinet, Profibus. So this is key to understand what nested communication can do. Here you have an example of a frame application. It's a programming tool. So the frame application in this example here is from Schneider Electric. And the DTM is from a sensor vendor. It's an IO-Link sensor, and this IO-Link sensor was connected via Modbus TCP, Profibus, and then IO-Link. And you see this DTM from this device integrated in your tool, and you can, from this tool, you can access the device, configure it, and diagnose it. So the standardization, FDT is a widely accepted international standard. So the first standardization we did was of course, in IEC, and then ANSI ISA 103 followed, and then some years ago we also had standardization activities in China, so it's also a national standard in China. Now I would like to talk about the OPC UA, how we worked on this. So what we achieved here is that we have a unified device model with OPC UA independent of the devices and networks. Here a short overview on the DTM information model. So these are the interfaces and information a DTM provides in his business logic, so not on the GUI side, on the device model side. And you see here information about the device, which is about what type of device is it, what vendor, then what are the data in the device, so the parameters, what are the process data, so these are the data which are normally transferred on the connected field bus. You have functions, so a DTM has a list of functions which you can call, for example, from the frame application, and these functions are offered in an interface. You have document references and so on. So these are the information model of FDT for a DTM. Maybe many of you know already the structure of OPC UA, which is the successor of the OPC standardization. OPC UA means unified architecture. It's operating system independent. And in OPC UA, you have a base structure where the base services are defined in OPC UA. Then you have some specific models, for example, data access, historical data for commands and these things. These are these orange building blocks. Then you have an additional specification in OPCA, which is called OPCA for devices. It defines a model for field devices, and on top you can add your own model, a vendor model. And for FDT, of course, we have done this FDT information model with a specific mapping from the FDT model to the OPC UA model. Here's the architecture in a frame application. You see here this box on the right hand. You see the frame application part with the DTMs and the physical layout as a schema here. And this structure is mapped into the OPC information model. You see it here in a similar way. And then any OPC UA client can have access to this OPC UA model, and we map the data from the OPC UA model to the FDT model, and we also can access via this structure and what I mentioned before, the nested communication. We can also access device data from the plant. This is the architecture as it's written in the FDT specification. So what we support today on the use cases, which we used for mapping this information, so they were the basis of the mapping work we had to do. So I will not go through all of this, but you see here, first you need the topology. That means you browse the OPC UA server to get all the objects out of the OPC UA server. We have then list of the devices. We can identify devices. You can get a status or diagnostic. You can read and write parameters and all the things. And here is an example for such a mapping, because the models are not the same. So the information model from OPC UA and our FDT model are of course different. So sometimes it's necessary that you map different information from FDT into one object in OPC UA. Here, for example, the device information. In the instance data of DTM, you have the serial number, and in the type information, you have the manufacturer. So these two information are then mapped into this object of object A of the OPC UA device model. And so we have done many of the things to fix this mapping. So where are we today? We have done a prototyping 2 years ago to integrating an OPC UA server and a frame application to verify the specification, to see how it works. You see here some prototyping. We had different OPC UA clients where we tested this OPC UA server. You see here 2 examples. This is on the market free available client from Unified Automation. Underneath we built our own client, which looks like an FDT tool. We also used a mobile device with the OPC UA client to access the server. So that works fine. And we have released the first annex. So annexes are amendments of the FDT specification, like protocol enhancements. So we are able to integrate any protocol in FDT. To do this, we define so-called annexes. In these annexes, we define what of this protocol is used in an FDT system. And here, we did it for OPC UA. And of course, work never ends. So there is a next step planned where we want to include more features and more possibilities. And as I said at the beginning, what we achieve here is a unified model of device model for an OPC UA client, independent what field bus the device is on and which vendor, from which vendor is this device. When you look today on all the OPC UA definitions, each field bus organization is doing its own OPC UA model. And here you have one model for all the devices. So this, because otherwise I think the client, the OPC UA client, has now to understand the different models. We have access to all these devices through this nested communication, and we can integrate also installed base into an Industry 4.0 environment. So if you want to integrate an existing plant into an OPC UA environment, you can do that. You install a system with the DTMs and the OPC UA server, and it runs. The installed base is not harmed or changed, because we use the standard protocols, the standard field bus protocols. We do not change anything on the protocols and the devices. Now the next step we are working on is the management of the field devices using mobile devices like tablets or phones. And here we have a scenario which we want to use in the first step. We have a mobile client. Your customer or maintenance guy is standing in front of your device and wants to have some information out of this device. And we have here an FDT application as a server where the DTMs and the business logic from the DTMs is installed. So we are able now to talk via this mobile communication to the server, and from the server we use the nested communication to access, for example, here a CANopen device, even if a CANopen device is not able to be used with a mobile device. So we can, all devices, CANopen, Profibus or whatever, we are able to provide a mobile access in a standardized way. It's always the same behavior and the same look and feel if you want. And the requirements here we had is, okay, we want to reuse the business logic of the existing DTMs. This was important. The nested communication must be possible as it is today. We do not want to change anything in the plant, so it's as it is. And therefore, we think it's a nice functionality for the future, where we're currently developing a concept. Today, we have a client-server architecture in the FDT specification, but this architecture is in a way that the protocol or the data exchange between the client and the server is not standardized. So normally, the frame and UI and the frame business logic have to be from the same company that it works together. In the new architecture now, we will change that. So we will still have, of course, the existing solution with the rich client and the FDT server with the business logic, but we want to add different possibilities of clients. So a thin client working in a browser, where we provide a mobile DTM UI with HTML5 and JavaScript, or we use a hybrid application app, for example, PhoneGap or others, and using there an app for the device, or we can even have specific apps. For example, if a device vendor wants specific features for his maintenance people, which are not the customer, he can also develop very specific apps. And in the server, we need some enhancements. So we will have a web server. We will add HTTP secure connections, but also WebSockets, because you need WebSockets for permanent data exchange and between client and server, and not always opening and closing the HTTP connection. And we are able to add some additional features which can be provided by a device vendor of providing the DTM. And all these interfaces you see here, the orange ones, will be standardized. So what are the status today? So we have defined the requirements by our technology marketing team. We did a survey several years ago now, 3 years ago. We started an online survey with many participants to get out the requirements. And we also did some end-user interviews. We had workshops with FDT and mobile experts to outline this architecture I showed you before and define the prototyping. Now we will start this month with a prototyping with 2 different scenarios to check what is necessary to take into account when we do the specification. So we have to update then the FDT specification, the next step, and this includes also a style guide. So the style guide is a DTM style guide we have today, which describes the main look and feel of a DTM. So not the detailed content, but how a DTM has to look like, so that the customer always has the same look and feel and behavior. And we have so-called common components. We discussed this morning about interoperability and standards. So we decided in the FDT group to have a component, a black box, which is provided to frame developers, and we have the same for a DTM, and these 2 components are tested very intensively, so we are very sure that the applications with these components are highly interoperable. So now coming to the end, the next step is what we call FITS, FDT IIoT server. So with the new concept, having here the business logic part of the frame and the DTMs, we are able to move into other areas than on a PC. So we could be ready to go into a cloud or in a fork, because we have web services where we can access the devices via web browser or via mobile devices. We have the OPC UA providing information to the upper layer like ERP or asset management system. And of course we can add new protocols, for example, to access our control level. Here you see, for example, a VPN, so this could just be a gateway DTM providing a VPN connection, or we could also have a gateway DTM, providing an MQTT protocol as it's used more and more in the IIoT environment. Yeah, so my conclusion, FDT is really able to be combined with other standards, which is very helpful. So we do not invest and invent everything new. We use what is there for future steps. And what we provide is a standardized device management in the field. We have now a unified device model we can provide to other systems. We are network and field bus independent, so it's no matter what field bus it is, we can integrate this. We have this nested communication so that we are crossing more than one level in the network. It's extensibility, as I said before, we can add, for example, MQTT with the new annex. We can also enhance the installed base with these new technologies. So you just create an application, a frame application with these DTMs, and you can have access to existing installed base, providing new features like mobile device access. So, and we see us also as a bridge to IoT and Industry 4.0. Thank you very much. And do you have any question?
Thank you. Any questions from the audience?
Yeah, Christian Schlegel, HMS. One question when it comes to these gateways.
Yeah.
For example, if we have a gateway from Ethernet to CANopen, does the gateway need to have a special functionality implemented to act as an FTT gateway?
No, it's the other way around. The DTM has to work like the gateway. So if I'm a gateway manufacturer and I want to provide a DTM, gateway DTM, I know what to do with my gateway. So I communicate with my gateway. Nobody else has this knowledge and need this knowledge because it's covered through the interfaces, and the functionality is done in this gateway DTM in coherence with your gateway. Same like other devices.
Okay. Other questions? Okay, so if not, thanks again.
Just one hint, we saw before the XML description for CANopen. So what you also can do, and what we do is, we have so-called generic DTMs. These are DTMs which interpret a device description, so you don't need to write a specific DTM. It's a generic DTM which can interpret, for example, device descriptions. That's also the first easy step to go into the technology.
Okay.
Thank you very much.
Thank you.